Yeah, so as I was saying yesterday, going on about the sort of Venturi effect, with the Venturis and the choke that are in there creating a vacuum, which in effect then pulls the fuel through the jets, which then mixes with the air, and then you get your stoichiometric 14 to 1 ish fuel air ratio in the engine. So I was going to show you from sort of first principles how a carb works. A lot of people might think that the fuel that comes in through the top of the carb into your float chamber, through that, which is fed by a fuel pump, is what effectively forces the fuel into the car, into the engine, but that's not the case. It acts, the Venturi effect of the carb is the thing that actually does that. So if I basically show you from first principles how that works, going back to my uni days and Bernoulli's equation, I'll show you now on a bit of paper. So what Bernoulli's equation says is pressure 1 plus rho g h1 plus half rho v squared v1 is a constant. So P1 being, in this instance, the pressure, the atmospheric pressure, all of these are in SI units, so that's Newton per metre squared, that's kilogram per metre cubed, that's the force of gravity newtons per kilogram, height in metres, same with the rho there, and then your velocity is in metres per second. So what effectively that's saying is your your pressure 1 outside, density of your air, gravity is 9.81 newtons per kilogram, height is in meters, again your density of your air outside, and the velocity of the air that's entering the initial part of your Venturi, being it's a 45 DCOE carb, should find it's 45mm diameter. Which, yeah, okay, thereabouts. And inside, you probably can't actually see, but on that choke, just back behind the main Venturi, it's 36, so that's 36mm restriction. And what in effect that does is it creates, accelerates the air that's entering, which creates a pressure drop, which I'll show you how all that works now. So basically, for Bernoulli to work, if I use the pump as a bit of an example, if you've got a pump going through, it assumes that the conservation of volume. So if I'm pumping air through this valve here, then the flow rate of that air going through is constant. So if I restrict it, the volume that is going through, because it's fixed, is the same, but the velocity which it comes through when you restrict it increases to compensate for that change in area. So with so basically your area 1 times your velocity 1 is always going to be a constant, because you're not in a fixed system, you're not losing air out the system, so any air that's going down into your chokes and into your engine, you're not bleeding any out, so it always has to remain the same, the volume of air that actually goes through. So basically, if we're saying that 1 is the point outside here, then inside, sort of this side of the throttle, is going to be, say, A2, so that's always a constant regardless. Area is in meters squared, velocity is in meters per second, so that's volume of meter cube per second, and that's your volumetric flow rate. So the constant, that's always going to be a constant no matter what when you've got a closed system. So A2 V2 must also equal A1 V1. So in this example, so you got P1 plus rho G H1 plus half rho V squared, and that's V1 squared, must equal at your throttle side, P2 plus rho GH2 plus half rho V2 squared. Now the height is always going to be the same, so this is a fact. If you've got like a pipe and you're trying to work out what the pressure drop is at the top and the bottom, then you've got to change in, so you've got your velocity head, your height head, and your pressure head. Heights are going to be exactly the same at the start of the carb as they are at the back of the carb, so in effect those two cancel out because there's no effect. So if you're trying to work out what the pressure drop at the venturi is, which pulls your fuel into the engine, into the carb, you're trying to basically work out what P2 is. So if you rearrange this equation, P1 plus half rho V1 squared minus half rho V2 squared equals P2. Now in this instance you're gonna know what P1 is, because atmospheric pressure, which is 1 times 10 to the 5 newtons per meter squared, or 1 pascal. Density of air, you know. V1 you can measure with a flow meter outside. Now you're not going to know what the V2 is because it's obviously inside, and it's the V2 that governs the pressure drop. Well, not just V2 that governs the pressure drop, but you want to know what the pressure drop is at the venturi. So as I said before here, if you're trying to work out what P2 is because you know P1, in effect if you rearrange this lot, you get your area 2 divided by your area 1 times I've done it the wrong way round, forget that. So if you rearrange this to get V2, so V2 equals A1 divided by A2 times your initial velocity. Now you know what your diameter of your choke is because I just measured it, 45. You know what the diameter of the second choke is because it says on there it's 36. So you can basically work out through pi r squared what the area of both of those two are, and then you know what V1 is. So if you rearrange this equation to include V2 as a function of V1, you get P1 plus half rho V1 squared minus half rho, so V2 is A1 divided by A2, and then multiplied by V1, and then that lot is squared. So again, if you rearrange that lot, you get P1 plus half. So now it's all a function of that, and you can pull that V2 out. So you get half rho V1 squared minus half rho V1 squared, and then multiplied by A1 divided by A2, and that's squared. And then you can and that equals P2. So you're basically left with that equation there, and what you can do is if you rearrange that, you'll get half rho V1 squared bracket 1 minus A1 over A2 squared equals P2. So your pressure drop at that venturi position is governed by your area of the ratio of your area outside to the ratio of the area at that choke. So if you've got P1 at say 1 times 10 to the 5, you're adding this part of the equation to it. So if your ratio of A1 divided by A2 is, the greater that differential is, then once squared, once you minus that from the 1, you're likely to be left with a negative number, which will make all of this here a negative number. So when you add it to your P1, you'll get P2 being less than P1, so therefore you get that pressure drop. And you can do it if you do the maths, some numbers in for this example. P1 is all in SI units, as I said, 1 Pascal, which is 1 times 10 to the 5 newtons per meter squared, plus half times rho, roughly 1.2 kilogram per meter cubed for air. Assume a intake velocity of 5. Fuck me, if I get interrupted one more time doing this, I'm gonna fucking smash someone up. So assume an intake velocity of 5 meters per second, and then you do 1, your area. So you want to work out your area of your A1, which is as we said 45 mil, so 22.5 times 10 to the minus 3 squared times pi divided by the 36 mil Venturi, so that's 18 times 10 to the minus 3, so that's your R squared times pi. Don't need to worry about pi, cancels out, squared. So if you do work at that bracket first, so 22.5 10 to the minus 3 squared, store that as A, 18 times 10 to the minus 3 squared, put that as, store that as B, so do alpha A divided by alpha B, gives you that, square that, store that as alpha A, 1 minus that, gives you minus 1.44, store that as alpha A, and then do your 1.2 times 5 squared, 25, divided by 2, multiplied by alpha 8, gives you minus 21.62, and that's in newtons per meter squared. And then you do 1 times 10 to the 5 minus 21.62, 1 times 10 to the 5 minus 21.62, and you're 78.38 newtons per meter squared, which equals P2. So P1 was 1, 0, 0, 0, 0, 1, 2, 3, 4, one more, and your P2 x5 minus alpha A equals 21.62 is your pressure drop, which then pulls your air into your system, mixes, sorry, your fuel into your system because of the pressure drop. So in effect, when you look at this, as I was saying before, the greater that you could make this whilst maintaining the same V1, the greater the difference. So 1 minus a massive number will create a really negative number. So the greater that you can make this ratio, the greater the pressure drop is. So if A2 is huge, so if you went down to, say, I don't know, 1 mil diameter, that will be quite big because you square it. So if it was 1 mil, you're left with an area of, you know, you still got your 45 mil A1 diameter. That'll be huge. The pressure drop will be massive. and therefore the pressure drop within there will be big, drawing in more fuel. So that's in effect, through Bernoulli's equation, how a carb works. Enjoy.